Good afternoon. My name is João Moreira, and this is my presentation on a survey on existing legged-wheeled robots. In this presentation, I would like to start by motivating the need for these systems by talking a little bit about the potential of robotics in unstructured environments. Then, I will mention why legged robots are suited for these scenarios, and what advantages hybrid systems have over purely legged ones. Finally, I will talk about the lessons learned while researching on this topic. More specifically, I'd like to mention the most salient design aspects noticed in the choice of kinematic configurations, general hardware, and actuators. Currently, robots are widely used in controlled environments, such as factory floors and warehouses. They perform fast and with precision, allowing repetitive and exhausting tasks to be executed effectively. This effectiveness is a testament to how useful robots can be if they are adapted to unstructured environments, where they can help replace humans in demanding or unsafe conditions. For example, robots can be used in search and rescue missions to perform initial reconnaissance of a dangerous location, or they could be used in planetary exploration to lower the risk and cost of sending people where it is not strictly necessary. However, developing these systems capable of moving in unstructured environments presents some challenges. Robots of this kind need to be able to navigate these environments, interact with humans, and have forms of locomotion suitable for non-flat terrain. One form of locomotion which nature shows is very versatile is leg locomotion. Unlike wheels, legs allow a robot to step or jump over obstacles. Legged robots also have higher autonomy than flying vehicles, like drones. They can also carry heavier payloads. Overall, their versatility and usefulness make them reliable candidates for locomotion in unstructured environments. Despite their versatility, leg-based solutions can be improved upon. Since wheeled vehicles are often faster and more efficient, hybrid solutions are able to combine this with the ability to traverse difficult terrain. This solution has been implemented in many robots so far. The intent of the survey is to show some of these robots' traits and to try to capture common design philosophies used among them. The robots that were surveyed are the ones in the list. The first aspect of these robots that was explored was their kinematics. Starting with the number of legs, it varied between 2 and 6. Dual-legged robots are obviously simpler to model since they have less degrees of freedom. However, they need to be actively balanced and are inherently less robust to disturbances. On the opposite end, 6-legged robots are capable of walking by moving half of its legs at a time while maintaining static balance. The obvious disadvantage is the increased modeling complexity from the added degrees of freedom. Most of the robots on this list show us that neither simplicity nor stability are more relevant than the other. In fact, 4 legs seem to be the sweet spot for most of these systems. Overall, it is sufficient to maintain static stability, and the extra leg helps with symmetry and disturbance compensations. Given these advantages, many designers seem to agree that an extra number of legs is unnecessary. Regarding the design of each leg, none of these robots is built with different ones. There is no distinction whatsoever between anterior or posterior legs. Even though the animal kingdom seems to benefit from this separation, most authors dismiss this possibility, perhaps due to the added difficulty in implementation and manufacturing. One aspect that does change across each robot is the number of degrees of freedom. There are those with just 1 degree of freedom in each leg. They use it mostly to move the foot vertically and take advantage of the extra motor in the wheel to move it longitudinally. Of course, this means that a pure walking motion is not possible. With 2 degrees of freedom, this problem is solved, but foot placement is limited to the sagittal plane. At 3 degrees of freedom, foot placement can be chosen in 3 dimensions, as long as one of the axes is misaligned with the other 2. The most common configurations for these three axes are roll pitch pitch or yaw pitch pitch. The roll pitch pitch configuration is also known as the mammal-like configuration, and it is more suitable for legged robots that need to perform more dynamic movements, such as running or jumping. The yaw pitch pitch configuration, also known as the spider-like configuration, usually provides a robot with a larger support polygon and increases its payload capacity. Beyond these 3 degrees of freedom, it is common to see additional ones that aid in reorienting the wheels. This can be helpful for omnidirectional driving. Overall, there are some factors to consider when choosing how to design a leg. Some, like modularity across legs, seem to follow a trend, while others, like the axis of rotation of each degree of freedom, are highly dependent on the design goal. Moving on to general hardware characteristics, most robots seem to have between 1.5 and 2 hours of autonomy, despite their large differences in size and weight. Considering that batteries come in great varieties, it is likely that they were chosen so as to achieve that level of autonomy for each robot. This tells us that designers seem to agree on what is enough time for these systems to perform their operations, and that investing money and weight in additional battery capacity is a waste. As was already stated, the size and weight of each robot varies widely for different applications. The heaviest robots tend to have a higher payload capacity, ranging from 60 all the way up to 350 kilograms. Some of these were designed for planetary exploration, which justifies their need for a high payload weight. The smaller robots are often not designed to carry any equipment. However, to give us a general notion of what their capabilities are, the lightest robot on this list is capable of carrying 1 kilogram. Unlike what happens with payload capacity, speed is not as related to the dimensions of the robot. Smaller robots tend to be more agile, and it is safer for them to move at faster speeds. However, the lightest robot on this list is the slowest, while the heaviest is the fastest. Overall, maximum speed is highly dependent on the application. Rover-like robots tend to move slower, since safety is of high concern. On the other hand, inspection and surveillance robots tend to be under less of a risk, while they benefit more from higher speeds. Generally speaking, most of these traits are incomparable, since they are strongly tied to the purpose of each system. Considering the variety of use cases for leg-wheeled robots, it is normal to find a high variability in these attributes. Within the hardware of the robots, some of the most important aspects relate to the actuating mechanisms. The joints of the robots listed are mostly made up of DC motors coupled to a gearbox, with some elastic element at the output. The use of such an elastic element in series with the output of the gearbox is often referred to as series elastic actuation. This is a commonly used actuator paradigm that confers these systems with robustness to impacts, making its use safer across a wider variety of environments. Additionally, if tuned properly, it can drastically reduce the energy consumption of the robot during cyclic motions, since it is capable of reusing energy stored in it when absorbing impact. Finally, if used properly, this paradigm can also increase the peak torque of the joint, which can also be useful for more explosive movements, like jumps, even though that is not the goal of most of these robots. Regarding power, as expected, there is a relation between how much each joint can deliver and how heavy its corresponding robot is. However, nominal speeds and torques can vary considerably. This is, once again, relatively normal, considering the different use cases for these robots. Besides the variations between robots, the variations between joints of the same robot are also noteworthy. Some of these robots use the same actuator for every joint. Much like with leg design, this modular philosophy constitutes an advantage in development and integration. The downside is that, compared to robots with dedicated actuators for each joint, a lot more mass needs to be carried further away from the base of a robot. This increases the inertia that the joints closer to the base need to move. Consequently, this increases energy consumption and has a negative effect on the maximum acceleration that these joints can reach. Once again, both design approaches are valid and should be considered according to the intended use cases, as well as personal preference. Finally, it is important to mention that some of the heavier-duty robots in this list are powered by linear actuators to accommodate for the higher torques required. This is yet another aspect proving that the versatility of these systems will create a large variability in these robots' designs. Hopefully you found these remarks useful for your next endeavors in the field. Thank you for your attention. If you have any questions or comments, please let me know about them through my email.